Hi, David Ken here with another question in 5.2. We're going to be investigating one or more of the factors that affect resistance experimentally. We have a cylinder with conductor length L, diameter D, and resistivity ρ. So it looks something like this. It has length L, diameter D, and resistivity ρ. As a result, it has a resistance R. Resistivity is normally rho L on A, but we're not given the cross-sectional area A, we're given the diameter, so we'll call that rho L on pi R squared. D on 2 would be the same as R. Simplifying the formula a little bit by squaring each term in these brackets, we'll get rho L on pi on 4 d squared. That's equal to R in general. In this case, the resistance of wire 1 is equal to rho 1 L1 on pi on 4 d1 squared. We're told of another case though, a different cylindrical conductor. It's twice the length and twice the diameter. So that's 2d 2L, and it has twice the resistivity, 2 rho. So for resistor 2, it also should have resistance times of its resistivity times its length divided by pi on 4 times its diameter squared. But its rho its resistivity is twice the resistivity of conductor 1, and the length is twice the length of conductor 1. And the diameter is twice the diameter of conductor 1. So this allows us to make a substitution. Rho 2 is really 2 rho 1. And length 2 is really 2 length 1. Pi on 4 stays the same, but d2 is twice d1. And when we take a look at this algebra, we see that we have 2 on 2, 2 times 2, that's 4 on the top, and we have 2 squared, that's 4 on the bottom, which means that this 2 cancels with these two 2's. Not because we can distribute the 2 into both, but because there's really 2 of the 2's on the bottom when we square it. 2 times 2 on the bottom and 2 times 2 on the top. And when we do that, what we arrive at is rho 1 L1 on pi on 4 d1, which is the same thing as R1. That's what we found before. What that means is that R2 is the same as R1. Yes, making the conductor longer increases its resistance, and yes, increasing its resistivity increases its resistance, but doubling its diameter reduces its resistance by a factor of 4, which cancels out both of those two factors. So the fast way to answer this problem is just to recognize that length has a proportional effect on resistance, resistivity has a proportional effect on resistance, diameter has a squared effect on resistance, or it has so it has twice the proportional effect. So this too reduces the resistance as much as this doubling and this doubling. So overall there's no net effect on the resistance, it's the same. Both of these have the same resistance.